we will look at one way of making a flip-flop out of FETs. In fact, there's a nested hierarchy. A flip-flop can be made out of two D-latches. A D-latch can be made from an RS-latch and some combinational logic, and an RS-latch can be made out of two NOR gates, and a NOR gate can be made out of FETs. Therefore, a flip-flop can be made out of FETs. These days, CMOS flip-flops are more likely to be made in a slightly different way using transmission gates and tri-state inverters, but nevertheless the key points are the same, so it doesn't matter if we look at this slightly old-fashioned way of making flip-flops in this course. An RS-latch can be made using two NOR gates. Normally R and S are both 0, and then the output Q just stays the same as it was. If S is 0 but R goes to a logic 1, that resets the RS latch, meaning Q goes to 0. And on the other hand, if R is 0 and S becomes a 1, then that sets the flip-flop and Q becomes 1. The output Q bar is essentially always the opposite of Q. The exception is if both R and S are 1, but we try to avoid this possibility. So normally when operating an RS latch, R and S are both 0 and the output Q just stays the same. To reset it, you apply a brief pulse to R to make Q 0. To set it, you apply a brief pulse to S to make Q equal to 1. A D-latch is made from an RS latch by attaching just a few more logic gates. When the enable pin is a 0, then the output of these two AND gates are both 0, and hence the RS latch is in its latched state, meaning Q just stays the same. If the enable pin goes high, then whatever is on the D pin will end up on the Q pin, because if D is a 0, then that's going to become a 1 through here. 1 and 1 is 1, and we get a 1 on the reset pin, which makes Q 0, and we get a 0 on the set pin. On the other hand, if D is a 1, then we've got a 0 coming in here, so I have a 0 on the reset pin, a 1 here gives me a 1 here, and I get a 1 on the set pin, which sets Q. So a D-latch works by when E is 0, the output stays the same. When E is 1, the output Q is just a copy of D. A flip-flop is made from two D-latches. The first one is called the master D-latch, and the second one is called the slave D-latch. And remember, a D-latch works when the enable pin is 0, the output stays the same. When the enable pin is a 1, the output is a copy of the input D. To analyze this, let's consider first if the clock is a logic 0. So I've got a 0 coming in here. That means that my second D-latch, my slave D-latch, its output is not going to change. It's in the latched state. So when clock is 0, the output stays the same. That's consistent with how a flip-flop should work. What does the master D-latch do when clock is 0? When clock is 0, its enable pin is a logic 1, and so the input D is continuously being copied to the output Q of the master D-latch. So the input changes, the output in here is going to change when clock is 0. Next, we have a transition. The clock transitions to a logic 1. This means that the master D-latch is going to remember the last value of D at the rising edge of the clock. Because the enable pin goes low at the rising edge, that stops the output from copying the input. The output instead remembers the last value of D it saw before the enable pin closed off. So at this rising edge, the value of D just before the rising edge, so to speak, is what gets output to Q in this middle point here between the master and the slave D-latch. The second D-latch is going to start to open up at the same point in time. That means that whatever is at this point in here between the two of them is going to be continuously copied to the output. But what's here, we just discussed, is the last known value of D just before the rising edge of the clock. When the clock is a 1, the value in here coming out of the master D-latch is not going to be changing. It's going to be the last value of D that was observed just prior to the rising edge of the clock. So even though the second D-latch is continuously transferring the input to the output, the input's not changing by virtue of the master D-latch here. And in this way, we have built a D flip-flop.